My father was a Hebrew teacher and tried to teach me Hebrew, and I resisted foolishly. So he hired a friend to teach me Hebrew, and the friend liked mathematical puzzles. So half of every lesson consisted of mathematical puzzles. So that generated my interest in mathematics. I think inequalities are at the heart of work in partial differential equations, and I sometimes say inequalities make the world go round. I worked on some interpolation inequalities, which I discovered had been done independently by Gagliardo, an Italian mathematician, and they're often referred to as Gagliardo-Nirenberg inequalities. And again, they turned out to be very useful.
Like most of mathematicians in elliptic PD of the maximum principle, where you worked a lot with the moving plane method.
Yeah, the maximum principle, which says that the maximum of solution of a particular class of equations occurs on the boundary. That's just a fantastic tool. Didas and I used it to prove some symmetry of solutions for certain nonlinear elliptic equations. We used a method introduced by A.D. Alexandrov, a Russian geometer. And since then, people continue to use what we call the moving plane method to solve problems that I find unlikely to be solved using that method, but people keep coming up with new applications.
Some thoughts about your career being all at the Courant Institute?
I think I've had a very lucky life on the whole, getting the way I got there and having wonderful colleagues, wonderful students, wonderful friends in the world. Mathematics family is not a very big, but a very nice, warm family. Something really, to my mind, something really remarkable. We had visitors from Russia, of course, over the years. At one time, Olenek, a Russian woman mathematician, was visiting, gave a series of lectures. And she complained to me after a while that Peter Lax is sleeping in her lectures, which he often does. So at her next lecture, Peter wrote something on a piece of paper and passed it around. And it said, "We, the undersigned, testify that Peter Lax has slept through some of our best lectures." Everybody signed it, and it was given to Olenek at the end of the lecture. I told her she should frame it.
I would like to start with talking about what most us mathematicians encounter, the discovery of liking to math. So this usually happens early.
In my case, it did happen early. My father was a Hebrew teacher and tried to teach me Hebrew, and I resisted foolishly. So he hired a friend to teach me Hebrew, and the friend liked mathematical puzzles. So half of every lesson consisted of mathematical puzzles. So that generated my interest in mathematics.
Were they in Hebrew or in English, the puzzles?
They were in English.
And how is your Hebrew now?
I never learned Hebrew, alas. I resisted it. I regret it now, of course, but
You did your education in Canada, Montreal?
right. Well, I started in where I was born, in Hamilton. No, I started actually in another town. Anyway, I did most of my education in Montreal, including college. I went to McGill University.
And were there any memorable math courses you took there, or?
I sort of majored in math and physics with the idea of becoming a physicist. And there were good teachers. There was one mathematician who was still a very active mathematician. He did number theory. His name was Gordon Paul, and I admired him a lot. And the other people in the faculty, well, except for a young man, didn't continue to do research. They just taught.
And from McGill you came to NYU. Can you tell us a little bit about this move?
I graduated McGill in the spring of '45, and I got a job at the National Research Council, which was doing atomic research. And Courant's son was working there, one of his sons, a physicist, was working there, as well as his wife, whom I knew. She was from Montreal. And one day she said, we're going down to visit Courant for the weekend. I said, could you ask him where I might apply to study graduate work in physics? So she came back and said, he suggests, why not come and get a master's in mathematics, and then you might go on to physics. Mm-hmm. So I came down. I was interviewed by Courant and Friedrichs and was offered an assistantship. And I then just stayed with mathematics. So it was pure luck, pure chance, just incredible luck.
It's to the mathematic gains that you ended up with mathematics.
Yeah, I enjoyed very much the mathematics. I think I might have enjoyed being a physicist too. I have a great admiration for physicists.
At Courant Institute, at that time it was not called the Courant Institute.
No, it was just graduate math department.
Right. You did your thesis work with Friedrichs.
No, I approached Friedrichs because he was the most active research man in the department. Yes. And he suggested a problem, or a sort of vague problem, and I played with it for some months and got nowhere. Yes. And then Stoker, a geometer and applied mathematician, suggested a problem in geometry. So I started working on that problem, and that involved solving nonlinear partial differential equations. That's how I got into that subject. I spoke mainly with Friedrichs all the time. I learned more from Friedrichs than from anybody, and I still consider him my master.
The sensei.
Sensei, yes.
When you started working, whom did you start to work with?
Well, I first went to Friedrichs for a problem because he was somehow the most active person in the faculty.
Yes.
And he suggested a problem in spectral theories. So he suggested rather a field. Think about this. So first I spent some months, I got nowhere. And then I went to see Stoker, and he said, well, here's this old problem in geometry. Why don't you work on this problem?
Can you recall the problem for us?
Oh yeah, this was a problem that was originally worked on by Weil. It's called the Weil problem.
Okay.
So it's a problem about you have a sphere in two-dimensional sphere in 3 space. You have a Riemannian metric on it with positive Gauss curvature. Can you embed it isometrically as a convex surface in 3-dimensional space?
Right.
That was the problem. And Weil did some work towards solving it. He got some estimates, but he didn't get enough estimates to solve it. And so what I did was to fill in the remaining estimates that were needed in order to push through the proof.
So Stoker was your thesis advisor?
He was the advisor.
And whom did you interact with besides?
But I interacted mainly with Friedrichs, actually. I spent a lot of time talking with Friedrichs. I would like to say I got my degree in '49. The paper wasn't published until '53 because I was very slow at writing up my papers at that time. I had a bit of a writer's block. And at the same time, there was a Russian mathematician who also solved the problem, Pogorelov. So I would like to mention his name because he
but two things. I mean, going back to between 45 and 49, communication was not that good as it is now.
Right. So I had no idea.
When did you find about it?
I found out about his work after I'd written the thesis.
I see.
Yeah.
Then you finished your thesis and you were hired on the faculty?
I was hired as not as an instructor, something like
what we have here for instructors.
Somehow Courant's philosophy was different from most chairmen of math departments. In most math departments, the idea was somebody gets a PhD, then he goes elsewhere.
Right.
Or for exposure to other things. He may come back, may not, he or she. But Courant tended to keep the best students. I was away for a year. I had a National Research Council fellowship. I was in Europe for a year. Then when I came back, Agman came as a visitor for a while, and also Protter.
Right.
And we wrote a paper together. It was on maximum principle for hyperbolic equation, second order hyperbolic equation.
Now, okay, so let's talk a little bit about the maximum principle. You've done enormous work on that.
Yeah, a lot of my papers use maximum principle for elliptic equations, parabolic equation, and this one paper on hyperbolic
equations.
Let me just mention a story connected with the hyperbolic paper.
Okay.
Hans Weinberger was attending a talk given by Bochner somewhere, I forget where, and Bochner did something in this talk, and Weinberger raised his hand and said, "Oh, that follows from the Agman-Protter, Nirenberg-Protter maximum principle." So after the talk, he went up to explain, and he realized, no, he didn't have that maximum principle in mind. He had invented a maximum principle. Weinberger, intuitively, he thought there is a different maximum principle, which he then proved.
I see.
But, so
He mistaken your maximum principle to the one
for the one he thought of, and
very interesting.
which didn't exist before, and he proved it.
I did not know that.
So maximum principles I've used mainly elliptic equations. So the maximum principles enter getting all kinds of estimates for solutions, for the derivatives, for nonlinear problems, linear problems. There's a method which was invented by a geometer, A.D. Alexandrov, called the method of moving planes.
Right.
And this is a method to prove symmetry and monotonicity of solutions of certain equations where the equations have a symmetry, for instance, radial symmetry.
Right.
And some years later, after Alexandrov, this Russian, did it for his geometric problem, Sarin used it for a problem, and then Gidas, Ni, and I used it to prove a problem which Gidas raised. It came from physics. And we use this method of moving planes, and at the heart of it is the maximum principle. And there are different forms of the maximum principle. There's something called the Hopf lemma,
Right.
which says that if you have a solution of the equation and if its maximum occurs on the boundary and the solution is not constant, then it's normal exterior normal derivative there is actually positive. That turns to be an essential tool somehow in elliptic PDE. And also there's a parabolic version for parabolic equations, which
You
was
also
proved
work on
later
the
by
parabolic
Friedman.
equation.
Yes, I had
Maximum
one. Yes, I had a paper on maximum principle, this so-called strong maximum principle for parabolic equations. Yep. So I learned essentially to work on elliptic PDE through the thesis. And so since then, almost all of my work has involved partial differential equations. From geometry or in complex analysis, it's all involved partial differential equations.
So, but there are other problems in geometry you worked on, the Nirenberg problem.
Oh, there's something that's been called the Nirenberg problem. This is to, again, look at a Riemannian metric on this two-dimensional sphere, and it has a Gauss curvature, and the question was, which functions can you prescribe on the sphere as Gauss curvature for some metric? So I posed that problem. I gave it to a student, and we solved. He couldn't solve it in general, but he solved the perturbation problem, where you're perturbed from constant Gauss curvature.
Right.
What he did was generalized later by Moser to a case where the Gauss curvature, this function is symmetric. And then the general case turns out to be false. Counterexample was produced by Kasdan and Warner. They found a necessary condition on this function that you prescribe as curvature. And since then, there's been further work. People have produced sufficient conditions, and people are still working on it. Now and then I get a paper, somebody So working on a so-called
Generated lots of
Nuremberg problem.
activity.
Well, some activity. I did a paper on rigidity. And so there's an open problem, classical open problem. You have a closed surface. Can you deform it continuously isometrically? That's an open problem. It's been open for 150 years, this problem. A counterexample was produced a few years ago of a polyhedron with corners that could be deformed continuously. But a smooth surface, it's not known. People had proved a number of years ago that a convex surface is rigid. Cannot not only deform it, but if you have two convex surfaces which are isometric, they are really the same surface in three space. And so I extended that result to something like a tube, like a tire tube. So it has some kind of tube connecting inside, and I extended that using partial differential equations, and I had an assumption that I needed, and I raised the question: do you need that assumption? And the assumption was, in this closed tube of negative curvature, can you have a closed curve which is asymptotic curve on the surface? And my theorem says assume you could only have one, but maybe you could have more. A few years ago, a Russian paper appeared showing that you could only have one, or none rather, but using analyticity. So it's still open in the general case whether you can do it. And then I mentioned this Alexandrov paper. What he did, he proved that if you have a hypersurface in Rn, which is embedded, closed, smooth hypersurface with constant mean curvature, then it's a sphere. And for many years, people tried to get rid of the embedding hypothesis. And then an American mathematician, Wente, gave a counterexample of a two-dimensional torus in R3, which intersects itself and has constant mean curvature. So
I did not know that.
Yeah, and then Yan Li worked on an extension of Alexandrov's theorem, and then together we worked on a different extension, which was if you have a surface embedded in Rn, hypersurface, and if you choose some direction, say call it direction xn direction, and if the mean curvature for two different points on the surface, if one lies above the other, the mean curvature, the higher one, is bigger than or equal to the mean curvature below, then what we tried to prove is that in fact they are equal and the surface, hypersurface, is symmetric about some plane perpendicular to that direction. So we proved that. In fact, it's a rather recent paper, but with some hypothesis, and we conjecture that that hypothesis is not needed. So there's another open problem, which I hope somebody will solve.
I mean, I know you've always been fond of Alexandrov's original work.
Yes.
Told me that it's a paper full of ideas.
Yes, and he did other things. He was an excellent mathematician.
Geometry, as I understand, has always been a subject that's dear to your heart. You like the
I
mathematics.
think it's a wonderful subject.
And you like many results in geometry that always fascinated you. Do you want to mention some of them that you liked?
The one I like best, of course, is the work of Nash, John Nash, on the isometric embedding of any Riemannian manifold on any Riemannian metric on any manifold, that you can embed it in a sufficiently high-dimensional Euclidean space. And he developed a method for solving it, which I found remarkable, truly remarkable. And later it was put in more abstract version by Moser, and Moser used it to obtain invariant curves for dynamical systems, and other people have used this method. It's a method rather than a theorem. About the Nash embedding theorem, some years later, a man named Matthias Günther found a proof without using that method. So the method is somewhat elaborate, but he found a proof in a more traditional kind of proof, which I found also quite striking.
It is indeed, it's very striking.
There's a long open problem that I try to tell people
Okay,
to try to solve. It's a purely local problem. You're given in the plane near the origin, say, you're given the Riemannian metric, smooth metric. Can you embed that as a piece of surface in R3 isometrically? That's the problem. It's still an open problem. It's true if the Gauss curvature of that metric is positive, then you're led to a nonlinear elliptic equation. If it's negative, you're led to a nonlinear hyperbolic equation. A student of mine considered the case where this Gauss curvature vanishes at the origin, but its gradient is different from zero there. So it vanishes cleanly.
Right.
And he was able to prove embedding. And then some further results have been obtained, but the general problem is still open.
Maybe we can move into the areas of complex analysis, which you've done major contributions there as well.
It's a subject I find very beautiful. It's was my favorite subject to teach. Recently I learned that Midwest University, in their graduate program for people working in differential equations, don't require students to take a course in complex analysis. I was shocked.
That's blasphemy.
Absolute blasphemy, yes.
Every student, the first they encounter it, they love it. So
Yeah.
it should be taught indeed.
I got into the subject involving several complex variables. So it was a question, suppose you have in 2n real dimensions, you have n first-order differential operators with complex coefficients, just higher-order terms,
Right.
which are linearly independent. Can you make a change of variable which reduces them to the Cauchy-Riemann equations in n complex dimensions?
Right.
And there are obvious necessary conditions for that. And a student of mine, Newlander, and I proved that these conditions were sufficient. And we did it in a kind of funny way. What you have, if you write down the equations analytically, it's purely local problem.
Right.
You start with the Cauchy-Riemann operators, and you add some additional terms. And so I suggested to him, look at the case where there's just one additional term in two complex variables. That means in 4 real dimensions. And he had an idea to do that. He saw how to do that. Then together we saw how to eliminate all other terms in 2 complex variables. And we thought, okay, we've solved the problem. And it turned out it didn't work in higher dimensions. So we came up with a different kind of proof, which was you're trying to introduce new coordinates as functions of the original ones. Instead, we said, look at the original ones as functions of the new coordinates. This leads to a nonlinear system.
Right.
But the nonlinear system that has better properties and that we could treat by solving the linearized equations and just iterating.
Right.
So the trick was to make it nonlinear.
Right.
Later, Hermander found a linear proof, and Malgrange gave a proof that I like best. It's a nonlinear proof, very, to my mind, very original, very remarkable. Because it's known that if the original problem, if the coefficients were analytic in all variables, I mean real analytic, not complex analytic, that you could solve it using Cauchy-Kovalevsky theorem.
Right.
What Malgrange showed is that you could introduce a change of variable, but solving some nonlinear elliptic problem, which reduces the new coefficients to analytic ones. Really remarkable idea. You would never think that would work.
No.
But it's really a striking proof.
If a student suggested to me, I say, no, don't waste your time.
That's right. It's a nonsense. Right.
Exactly.
You worked also on the Levy problem?
Hans Levy in connection with the problem, the two complex variables, came up with an example of a partial differential equation with complex coefficients, first-order equation in 3 real dimensions, with, in fact, it had analytic coefficients, and you want to solve the inhomogeneous problem. You're given the right-hand side. And for this equation, he showed that for any generic right-hand side, no solution exists in any open set. That came as a real shock to people in partial differential equations.
Right.
And then he posed the problem, could there be such an equation with 0 right-hand side for which constant is the only solution? And I came up with an example.
These are very interesting problems that I think I learned them when I was a student in PDE, the first few things about local solvability, which is, I know you like a lot.
Let me just continue with the problem. Later, Kuranishi looked at the higher dimensional problem. You have in odd dimensions, say dimension 2n plus 1, you're looking at n linear first-order operators with complex coefficients, and which commute with each other, say, or the commutator is a linear combination of all. And you ask, are there non-trivial solutions? Can you find a particular n independent solutions? So in the case when the little n was 1, that means you're in 3 dimensions, I showed there is no solution. He showed if n is 3 or more, there is a solution. Very complicated paper, remarkable paper. The case n equals 2 is still an open problem.
When was this work done? What year? Do you remember?
I don't remember. Maybe in the 60s or 70s. I don't remember. It's a very striking piece of work.
Yes. Any intuition why the 2 is so difficult and open?
No. People have tried, played with it. So far, nobody has come up either with a proof like mine saying that there are no solutions or giving solutions.
You did the work on Malgrange-Weierstrass preparation theorems.
Yeah, there was a famous old theorem in complex analysis called the Weierstrass preparation theorem, which is for complex analytic functions. It's a way of factorizing them.
Right.
And Malgrange gave a real version of it, assuming just smooth, everything smooth function. And his proof is very algebraic, and he does a lot of other algebraic things in the paper.
Right.
And I found an analytic proof which mimicked the original Weierstrass proof. Weierstrass proof is in complex plane, and he uses the Cauchy integral theorem. So what I did was to extend the function, which is not analytic, into the complex plane, where it satisfies the Cauchy-Riemann equations to infinite order on the real line.
Right.
And then I also use an analog of the Cauchy integral formula for solving the inhomogeneous Cauchy-Riemann equations, and managed to push a proof through like that. And the simplest case, I'd like to mention the simplest case. It's you have a complex function of n plus 1 variables, real variables. So there are n x's and 1 t. And the function vanishes at the origin, and its t derivative doesn't. Then, in this case, the theorem takes the form, you can write it as a product of a function which doesn't vanish at the origin times t plus a function of x, as in the form of the Weierstrass preparation theorem, except you don't have analyticity.
Right.
And such a simple thing. If you're working with real functions, it follows from the implicit function theorem. I don't know a simple proof for complex functions. My proof is not so simple. It's such a simple question, I don't know a simple proof. In fact, some years ago, for a semester, I ran a seminar called Group Therapy for Analysts. The idea of the seminar was people will come with
Yes.
problems, questions, saying, look, I seem to need a lemma that looks something like this. I don't know how to prove it. Maybe somebody in the audience can prove it. Or there's this known theorem in the literature. I don't like the proof.
Yes.
Maybe somebody can find a better proof. And a number of problems were solved that semester by people in the audience.
So people participated in
People
the discussion
participated,
instead
yeah,
of the...
So I came with a bunch of prepared questions, and other people formulated questions, and the number were solved.
Oh, that's a wonderful idea.
Yeah, I only did it once, but I regret that I didn't repeat it. But you have to have a list of problems to get it
Yes.
started.
Yes, an idea of proofs you want to simplify or whatever.
Or things you want that you think are true and don't see how to prove. Yeah.
Right.
So this is one such problem. There is a proof, my proof of this question, and can somebody find an elementary proof?
But this proof also has been standing as the only proof for a very long time.
Oh yeah, it's the only proof, yeah.
So if I can continue with the work on complex variables, you had the work with Kodaira and Koranishi.
No, that was Kodaira and Spencer.
Oh, Spencer, sorry. Oh.
Yeah, that was, they were looking at complex manifolds and deforming the complex structure. They wanted to see, using some topology, to what extent you can deform complex structure. And one of the things involved was to solve some nonlinear elliptic equations. So they came to me to ask if I could help, and I was able to help, and so we published that paper together.
Any other work in complex variables that you have done? You've done lots of work there, so any other work you're fond of?
Not so much, really. In connection with the Levy example, where an equation that had no solution for any right-hand side, François Trèves and I then looked at the more general question for higher order partial differential operator and postulated some condition which we thought was necessary and sufficient.
Yes.
And we could prove it was necessary and sufficient if the coefficients of the operator were real analytic. Then the C-infinity case for sufficiency was done by Beals and Pfefferman. But we had also formulated it for so-called pseudo-differential operators. And for that condition was slightly different. And that problem, the sufficiency, remained open for many years and was finally solved just a few years ago by a Swedish mathematician named Niels Denker. Rather elaborate proof.
All of these problems seem to be very difficult.
Well, mathematics is difficult. It's not an easy field. Though I love simple problems.
I know you like elegant proofs. You always told me that.
Well, of course, everybody likes elegant proofs, but
I mean, the first time I heard of ugly mathematics or beautiful mathematics was during a conversation with you. That not many people characterize mathematics in this way.
There was an important open problem about regularity at the boundary in several complex variables of the so-called D-bar-Neumann problem, which is, I won't go into what it was. And this was solved by Joe Cohn, very beautiful and elegant proof. Then we worked together to, this was an elliptic problem, but the boundary conditions didn't meet the usual conditions for regularity of the boundary, which were known. So he managed to solve that. And then we looked at more general problems of this nature, not necessarily coming from complex analysis. And we asked, can one get regularity? And for that, we had to use singular integral operators of Calderon and Zygmunt. And in their theory, they obtained some estimate for a commutator of two such operators. And we needed a double commutator, which wasn't in their theory. So we developed a theory which could do that, and that was pseudo-differential operators. It was a very natural outgrowth from the work of Calderon and Zygmunt. And that's proved to be a very useful thing, because people have used it in lots of problems.
we can go to the PDE topic,
Sure.
if we may,
Yeah.
which is, I'm aware that of your first work with Shmuel Agmon and Douglas on elliptic PDEs linear. Do you want to tell us a little bit how you got to work with them, your first time,
Well,
how you met Shmuel?
In fact, I worked with Agmon on a paper in linear partial differential equations, which was hyperbolic. And we proved a kind of maximum principle for that. That was one of my very early papers. And then I began working with Douglas on extending known theory for second-order elliptic operators to higher-order operators.
Right.
The theory was the so-called Schauder theory, Schauder estimates. So we managed to prove that in the interior of a domain, and we started to work on doing the same thing at the boundary. And then we discovered that Agmon was also working on that problem. So the three of us began to collaborate. And that developed into a rather elaborate, I must say complicated, not elegant theory. But the kind of estimates we developed have been used over and over again by people in the subject.
I mean, this is one of the seminal work in the subject, and it's been...
Well, these are basic estimates which people use, so, yeah.
Indeed.
Although, to my knowledge, almost no one has actually read the paper, except some Russians. I know
You
some
mean the
Russians.
paper of
Agmon, Douglas, and
Mirva?
myself. It's very hard to read.
I read it once. I mean, you have more than one with them.
We had two papers,
Right.
yeah.
And I read the first one, actually.
I see.
So
So
you can
were-
add me.
add
I'm
you
sure
to the
there are
group.
many
You don't
others.
look
but
Russian.
no, exactly. Your work, of course, in PDEs led to a series of inequalities, and many, many inequalities.
Yes,
You wanna
that's
reminisce?
I developed a love for inequalities, which I think I got from Friedrichs. And I think inequalities are at the heart of work in partial differential equations. And I sometimes say inequalities make the world go round. It's beautiful. I just love it. I hear a new inequality, I'm entranced. I worked on some interpolation inequalities, which I discovered had been done independently by Gagliardo, an Italian mathematician. And they're often referred to as Gagliardo-Nirenberg inequalities. And again, they turn out to be very useful.
Like most of mathematicians in elliptic PD of the maximum principle, where you worked a lot with the moving plane method and...
Oh, yeah. The maximum principle, which says that the maximum of solution of a particular class of equations occurs on the boundary, as you know. That's just a fantastic tool. And Didas and Lee and I used it to prove some symmetry of solutions for certain nonlinear elliptic equations. We used a method introduced by a geometer, A.D. Alexandrov, a Russian geometer. The method was used in a problem in geometry and turned out to be wonderful for doing this analysis for partial differential equations. And since then, people continue to use what we call the moving plane method to solve problems that I find unlikely to be solved using that method, but people keep coming up with new applications of the method of moving planes. I'm really struck by that.
It is
But the
a very
method
striking-
was introduced by Alexandrov.
Yes.
It was later used by Serin, and then Gidas, Nee, and myself used it.
Alexandrov, I think the paper, you're also very fond of that paper, and you always
Yes,
said it's a pleasure.
it's a beautiful paper,
It's a very...
In fact, Yen Lee and I extended the results of that paper to a more general situation, using the method of moving planes.
There are other topics that really quite fundamental in the theory of PDEs. That many of them are present in your little booklet on linear PDEs or nonlinear PDEs. One of them is the Cauchy-Kovalevsky, where you proved some...
Oh yeah, we extended from the abstract version of the nonlinear Cauchy-Kovalevsky theorem in an abstract setting, and that had been done before in the linear setting. And in fact, in 1941, a Japanese mathematician, Nagumo, had discovered that in the classical Cauchy-Kovalevsky theorem, where you have a variable time, and you assume everything is analytic and all variables he observed you don't need analyticity in time. He was the first to observe that.
That's in
And that-
1941.
in
you said?
1941, and that paper was unnoticed for years. It was published in a Japanese journal during the war. Only many years later did people discover that paper. But anyway, I gave an abstract version, which I thought was nice, but then a Japanese mathematician, Nishida, simplified my version. He threw out one of the hypotheses,
Okay.
wasn't needed, and so I recommend his version. And he applied it in fluid dynamics.
In fact, for a long time, this was the only way to prove certain local well posedness in fluid problems.
right.
Let's talk about the present day of mathematics. And in particular, let's talk about PDEs.
I think many of the people today who work in it are really working on specific applied problems. That is, specific equations coming up from either fluid dynamics or physics or even economics.
Right.
In fact, I wrote 2 papers with somebody in problems
Ivar?
coming from Ivar Ekland, problems coming from economics.
Right.
I knew and know nothing about economics, but he formulated them as purely mathematical problems, and we worked on them together. And we're still stuck on a third problem, this beautiful problem, which I don't know how to do.
But continuing in this vein is that, in your view, that PDE must have moved away from the theory part and more now into being part of other areas of mathematics.
I would say more people who work and use theory, PDE, are using it in connection with applications. So other parts of science, not so much in the theory of the partial differential equation. There are still problems in the theory, but there are not so many people working in the pure theory of partial differential equations. I mean, things coming from geometry, harmonic maps,
Right.
Yamabe problem, Calabi-Yau, and all
These are all been very
partial
active. Right.
Yeah, but they came from other fields.
There seemed to be a tremendous amount of preparation needed to train young people in PDEs because the amount of literature, progress, machinery that has been developed is really huge. And
Yes.
any thoughts about what will this do to the subject?
Yes, it's true. It's discouraging to a number of graduate students. So not many come into PDE because there's so much to learn, so much background. It's not a. I would say PDE is not a very. It's not a very clean field. It's a messy field. There, at the heart of it, are inequalities and other things. It's just, and you have to learn a lot. You learn harmonic analysis. You learn complex analysis.
Right.
You have to learn a lot of stuff in order to work in it. And it's messy, and part of the messiness, part of that is appealing to me. I like the messiness somehow. It's a feature I like. But for new students, very few students are going into it.
But there are also probably more students going into the problems involving PDEs in another area, like
Yes.
computations and
Yeah, in particular
Geometry.
computation, there are a lot of students who do theses in working on some differential equations, complicated differential equations, doing computing.
right.
So, which is very inventive. It's not that
Right.
something routine, but
No,
they
no,
have
no,
to-
right.
They have to cook up a good computing scheme, a good method.
Right.
There is some work also, you were talking about nonlinear Cauchy-Kovalovsky, on fully nonlinear problems you've done with Caffarelli and
Oh yes,
Something
Caffarelli
you
and
wanna give
Spruck
us,
and I wrote a whole series of papers on boundary value problems for fully nonlinear elliptic equations, starting with Monge-Ampère equation, and then going on to more general equations. That's very technical work.
Right.
The estimates are very hard, and these papers are not easy to read. They're not what I would call elegant papers. But
yes, but it's
also
the
with-
nature of the subject.
yeah, it's the nature of the subject. Also with Spruck and Kinderlehrer, I worked on problems of regularity of free boundaries. Kinderlehrer and Stampakia had done something in 2 dimensions, and then we extended to higher, Kinderlehrer and I extended to higher dimensions. And then with Spruck we did some related problems for free boundaries, regularity of free boundaries.
Your collaborative work with Louise started a long time ago.
Yes.
And it lasted for a long time.
It
So
lasted
maybe
for a long time.
you would like to elaborate a little bit about from the beginning of Louise.
Well, I must say I first heard of Louise from Hans Levy. Levy had visited the University of Minnesota, where
There's
Louise
some
was an
work
instructor.
also you were talking about.
Louise
nonlinear
attended Levy's
Cauchy-Kovalevsky
lectures,
on fully
and then
nonlinear
approached
problems
Levy
with
and
Donald
said,
Caffarelli.
"Could you tell me some open
Yes,
problems?"
Vicky, maybe you want to give us
Spruck and I wrote a
Which
whole
he did,
series
and
of
then,
papers on
to Levy's astonishment, Caffarelli came up with solutions to these long-standing open problems. So Levy was very impressed, told me about Louise, and then I urged that we hire him at Courant, and he came, and we began to collaborate on different problems. All of them are nonlinear problems. They have to do with existence theorems, difficult estimates. He has fantastic intuition, Louise. He sees things that I don't see, and he's extremely fast. So sometimes I had trouble keeping up with him. And that apparently is a common experience of people who work with him. He would write something on the board and not enough for me to understand. So I would say, "Louise, please write more, write more." So he would write a little more. And finally I used a sort of biblical expression, "Louise, where is it written?" But it was an enormous pleasure to work with him. The guy is so talented. It's just. But I've had many talented collaborators. It's just been a great joy.
Your work with Louise, did it start with the Monchampere or something else?
I think it started with Monchampere, with Spruck.
With Spruck.
Yeah. I had worked on Monchampere with Calabi some years before, and thought we had proved a theorem.
Yes.
And one day Pfefferman came to me. We hadn't published anything. Pfefferman came and said, "Can you show me how you prove the estimates?" So I showed him proof of some estimates, and then he said, "How do you get the lower bounds?" And then I realized I didn't know how to do that. We hadn't done it. And then I spent years just working on that and got nowhere. And then Louise and Spruck began to work on the problem, and I joined them. And we solved it by not getting those lower bound estimates, but different estimates.
And are these lower bounds estimates known to be true or
Yes,
not, still not known?
No, once you have the different
Then-
estimates,
then
it
you
follows
have
from
that
the general
particular-
theory. Yeah. So that was the first paper. And then we wrote a number of other papers on nonlinear equations. Fully nonlinear equations. Yeah. And then with Berezticki, we wrote on so-called semi-linear equations.
Right.
Several papers.
Right. You also worked about the De Giorgi problem with Berezticki?
In 2 dimensions we had solved it, but it had been solved by others. The problem we worked on was similar to the Giorgi problem, and there's still an open question there. In n dimensions in the upper half space, that means xn is positive. You're looking at a function u which is positive and bounded by some, let's say the least upper bound is a number m.
Okay.
And it vanishes on xn equals 0 and satisfies an equation of Laplacian u plus f of u equals 0. And the theorem we proved is that if f at the value m, the maximum of u, is less than or equal to 0, if I have the sign correct, then the solution depends only on xn.
Oh, right.
And I've tried for a long time to show that necessarily, if there is a solution, f of m has to be less than or equal to 0. But I haven't succeeded, and a number of other people have tried it and haven't succeeded. Still an open problem. Simple sounding open problem.
You also had a very long collaborative work with Henri Beresticki.
Oh yes, we wrote many papers together, some with Caffarelli on elliptic problems, and then we wrote several papers on propagation of waves in a channel or in a tube.
Yes.
And he has continued to work on that. I haven't, and he's done many other things, of course. But I must say I've enjoyed collaborating. That's one of the pleasures of mathematics to me. Working with other people is just pure joy.
Yes.
I mean, you interact with their ideas, they react to your ideas. It's just great.
In fact, most of your work is collaborative.
Yes, almost all my papers are joint papers. Yeah. And these days, I should work with somebody else because I make so many mistakes, some of which I catch, but not all. So my collaborators catch the others.
Any other work in PDE that there's the work, for instance, in fluids that is also in PDE?
Yes, I wrote one paper in fluid dynamics with Caffarelli and Bob Cohn on the so-called Navier-Stokes equations. These are equations of fluid flow in 3 dimensions, and there's a huge open problem whether if you start a fluid with smooth velocity and it develops in time, does it remain smooth for all time, or do singularities develop, such as turbulence? So that problem has been open for many years, and what we discovered is that in case singularities do develop, they have low dimension. They don't even have 1 dimension.
Right.
So, in some sense, low dimension.
This result, beside being fantastic and quoted enormously and very important, what I'm actually curious about is that you did not work in fluids before.
No.
And I don't think you worked in fluids after, except if you want to say the work with Beresticki somehow is related to some.
No, that's true.
So how does it come about? I mean,
I
did
remember
Bob
exactly.
Cohn come and ask you
No,
a
I
question?
remember exactly how it came about. The 3 of us were walking to Chinatown.
Okay.
And I said, you know, there's this interesting looking paper by, forgive me, I've forgotten his name, mathematician at Rutgers University, who was working on the singular set of solutions of Navier-Stokes equation and showed that Schaefer, and showed that they could have at most dimensions 5/3. And I thought, there's gold in them there hills, and why don't we work on that together? It turned out Bob Cohn had read Schaefer's paper. So he explained it to us, and we began working, and we lowered the 5/3 to 1 or anything, something less than 1.
Is there any other work in PDE that you're really fond of, which we forgot to mention? Or?
Yes, I wrote some papers with Brésis, a number of papers on nonlinear problems, solving boundary value problems.
Well, you collaborated with Brésis as well on problems with degree theory that I would like to come to after we talk a little bit about the BMO work with Fritz.
Oh, yeah. Right.
So maybe we can move then to the BMO work,
Sure.
if you don't mind, and tell me what, again, this is one thing that there's fundamental results in analysis, in classical analysis.
Fritz John was working in elasticity theory, and he came up with a class of functions that he called bounded mean oscillation, BMO. And he believed that these functions belonged to LP for every P. But he couldn't prove it. So he approached me, and I was able to prove it. And then he improved that. Not only was it an LP for every P, but also it was better. Let me not say technically how it was better. And I think that's an elegant paper, I must say. And it makes use of the Calderon-Zygmund decomposition theorem.
Right.
It has been extended. There's something called VMO, vanishing mean oscillation, which is a slightly stronger condition, and that turns also to be a very interesting class. If you look at continuous functions and you complete them in the BMO norm, you don't get all of BMO, you get that class called VMO. So it's a very natural class. And Brésis and I extended degree theory of continuous maps from one manifold to another to VMO maps. And we did it not just out of curiosity, but in some applied problem. Two French mathematicians, Boutet de Monvel and someone else whose name I've forgotten. They were working on some Sobolev space of maps, and they somehow needed degree for that, and they showed that it made sense to talk about degree for that Sobolev space. They were working on functions on the circle which belong to the Sobolev space H1 half. So these are not continuous functions, but nevertheless degree could be defined.
Right.
And so Brésis and I started to look at a more general situation, and it turned out that what was needed for was the notion of VMO, maps which are VMO. Maps which from Rn to Rn, whose first derivatives belong to Ln, are not necessarily continuous, but they do belong to VMO.
The BMO turned out to be also very useful in harmonic analysis as the dual of H1 of Hardy.
Yes, dual of the Hardy space,
Right.
H1. Right. That was discovered by Pfefferman.
But the discovery of BMO was totally between you and Fritz.
Well, it was Fritz who formulated the notion.
Fritz who formulated the notion, but it found its
way.
And
it came from elasticity
And it came from elasticity.
Yeah.
And I've always found this fascinating, that how something comes from you work with Fritz and then it's used somewhere else in a completely different subject. Now, of this work, there must be, I know many of the work is really quite difficult, and some of it is actually, as you say, it's not an elegant proof. Some proofs are elegant, but there must be also some works which may be very beautiful and elementary. Can you tell me about if you encounter something like this?
There is an elementary paper I wrote with Philip Hartman, which gave me enormous pleasure to work on. And it's in geometry. A particular result of it is if you have a function in the plane, and you look at its graph, the surface, if the Gauss curvature of that is 0, then this surface is a cylinder, global cylinder. And we gave some higher dimensional version of that. And we just had fun working on this paper.
And is it elementary and elegant, or?
I think it's elegant, yes. I think it's elementary and elegant, yes.
I don't know that paper, but it sounds like... And the fun came from the mathematics of trying to...
Yeah, just the fun of working on it. It was just a lot of fun, yeah. We did it by mail.
That's an old-fashioned way these days to do.
That reminds me, I wrote one paper with Peter Lax on stability of numerical systems. That was done entirely by mail. I was in Japan, he was in New York, and we did it by mail.
You mean all these years you've been with Peter since your school days, graduate school, you never worked with him except when you went to Japan?
That's the only paper that we wrote. Yeah. Let me mention one more paper. Yes. It's a paper I wrote with Beresticki and Varadhan.
Oh, yes.
I wrote only one paper with Varadhan.
Yes.
And it had to do with finding principal eigenvalues for elliptic operators in arbitrary domain, general domain. And it's interesting how Varadhan entered the picture. Beresticki and I were working on this, and we went several times to Varadhan with a question.
Yes.
And each time he said, oh yes, that's clear probabilistically. Let's see, how do I explain it to you? And then he found an analytic proof. At most, it took him 24 hours to find an analytic proof. So he became a co-author. And that paper is often quoted.
It's quoted very, very often, actually, in this theory.
So instead of going into mathematics, you brought up Italy, and I know you're very fond of Italy.
Yes.
And you have
Yes.
many Italian mathematicians and non-mathematicians close friends. So let's talk a little bit about your connection to Italy.
Right. Well, the first meeting I went to was one in Trieste in 1954. It was organized by a mathematician named Ficera, who was there at the time. And I had visited Italy before, had fallen in love with it, and Courant in 54 told me that he's arranging a meeting. He was invited to that meeting and he was asked to invite some other people to join. So I said to him, please invite me.
Yes.
So he did. And so there I met essentially all the young people working in partial differential equations. And so we became very good friends. Sampacchia, Magenis, Bucci, as well as Ficera. We became good friends, and these friends have lasted all my life. And since then, I've gone back very often to Italy and have many friends there.
Right. I mean, if I may now tell the story, is that you were very surprised when I was a Courant instructor here. We were talking about Italy, and I said I've never been, and you were appalled at the idea that I've never been to Italy, and you arranged for me a trip to Italy to visit.
Oh, I didn't remember
Absolutely,
that.
to Pisa, to Scuola Normale, and to Roma to visit Umberto Mosco.
I see.
So my first trip to Italy is due to you.
So I'm
And
proud.
the same,
to have done that.
which I became also very fond of. But this relationship of yours flourished over time and continued.
Oh yeah, it continues to this day. I've had two students from Italy, both young ladies, who are
Yes.
doing very well. They've returned to Italy. They're both have very active careers. You know, there's a story about Einstein. Apparently, he loved Italy. Somebody asked him, "What do you love about Italy?" And he said, "Pasta and levi civita."
You've gone into many meetings and had many meetings in your honor and your birthday and this. Tell me some of the meetings that you really enjoyed.
Well, the Italians organized summer courses called Cime.
Yes.
And I think it was at the first one that I spoke about this work that was Gagliardo did at the
Right.
same time. In fact, he was there in the audience. I met him there for the first time and learned he had done things on interpolation. And it was a very nice meeting. It was the lectures were held in different towns: Pisa, Lucca, and even the island of Elba.
Oh,
And Mori, C.B. Mori of
Yes.
Berkeley was there, and there was a photograph of him in the Pisa newspaper standing in front of a blackboard, and underneath it was written, lectured by Professor Nierenberg. So he looked at this photo and he said, "That's not Nuremberg, those are my formulas." And the Italians complained about his English because he would use expressions such as, "Well, if you try that, you don't get to second base." They had no idea what this was about.
okay. But
But he was a wonderful mathematician. He was one of the great
Mori.
creators of elliptic partial differential equations.
Another country that you are very fond of is China. And I know you were one of the first U.S. mathematicians to visit China.
I had a sabbatical in 75, 76, and Chern arranged that I spend 3 weeks in China. The Cultural Revolution was still on, but somehow I wasn't aware of it. And for instance, I visited the university, and I thought they would ask me to give a talk, or I would meet some. I said I would like to meet the faculty. And they said, "Oh, the faculty is very busy teaching the students." Complete falsehood. They were not teaching anybody. He just wanted to show me the library and the campus. So, but I gave a number of lectures at the Academy of Science.
So you mean you were not aware of the Cultural Revolution still going on?
Still going on. I thought it had finished, but it had not finished. Yeah.
I presume there you met some of the mathematicians that became long-time friends.
Sure.
As well.
Again, I have good friends from that time, and every time I go to China, I see them, and some of them come here. And
Was Casey Chang at the university?
he was one of the first visitors who came. He was at my lectures. He, as he explained later, got permission to attend them, and at the time they wanted me to give many more lectures, and I said no. I would like to hear what people here are doing.
Yes.
So some people told me about the work they were doing. And he was the first visitor from China and spent an academic year, and we became very good friends. When he arrived, I said to him, you have an opportunity to see classic foreign movies, which you could not see in China. So I gave him several movies to see. And he went to see, first one he saw was La Strada by Fellini. And I said to him, how did you like it? And he said, why do you like it? And I said, I gather you didn't like it. Why not? He said, it doesn't have a moral. Very odd reply. And then he saw Les Enfants du Paradis, Children of Paradise. I asked him, how do you like it? He said he liked it. And my wife said, he just wants you to get off his back.
You made many, many trips to China, even the recent ones.
Not so many, maybe 4.
But this change in it must be striking between
Oh,
75
a remarkable
and
change in Beijing and Shanghai. It's just incredible. And since I was there, I mean, again, there's been enormous change.
being one of the first to go to China at that time, and relations at that time were still not really normal. Were you debriefed or briefed before going, to telling you what to expect and not what to do or something like this?
No, actually not.
No.
No.
When you came back?
No, when I came back, no. On one of the trips to Moscow, I had mentioned to somebody from, I guess, CIA came to debrief me because I had visited an institute that does classified work. The visit consisted of the following. A friend working there said, why don't you come and visit one day? So I went, and it turned out he wasn't there. Okay. So I arrive in the lobby, he's not there, and some mathematicians come out, including Sinai's wife. And she says, why don't you come to our coffee room? So that was my visit to this, to the place where they do secure classified work. And then I was debriefed about that.
By the CIA man?
By some CIA person, yeah. Let me just mention, in Russia, 2 mathematicians were rectors of university, Moscow and St. Petersburg. A.D. Alexandrov was the rector at St. Petersburg, and Petrovsky. He was rector for a number of years. And when he was rector, the university really thrived. He hired people independent of their backgrounds, just based on talent.
Great.
And when he resigned, that changed, unfortunately. The first time I went to Russia was in 1963. It was to a joint conference in partial differential equation, joint Soviet-American conference. Courant was one of the organizers on this side, and Lavrentiev, organizer on the Russian side. And it took place in a town in Siberia called Novosibirsk. And there's an academic city there, and it was at that place. It lasted 2 weeks, and there were about 24 Americans and maybe 120 Soviet mathematicians from all over the Soviet Union. And it was like being on a ship for 2 weeks with people. You make friendships immediately. So indeed, it was full of warmth. I remember in the evenings, some of the Russians would walk us to our hotel. Naturally, we were at different hotels. Some of the Russians would walk us to our hotel, and then we would walk them back to their hotel, and then they would walk us back to our hotel. It was just a meeting full of joy and delight at meeting each other. They, almost all of them had never met any American mathematicians. So it was just a wonderful thing, and some of them have remained friends to this day. I'm going in June to a 90th birthday party of one of them in Moscow, Vishik, Mark Vishik, just turned 90.
At that time, the Soviet Union was quite still isolated from the West.
Oh, yes, certainly.
Not only politically, but I would imagine also scientifically.
Well, the Russians were much more aware of what the West was doing than we were of what they were doing. They got Western journals, and they ran seminars on papers, foreign papers, and on that occasion I visited Moscow.
Yes.
And I would say at that time that was probably the greatest mathematical center in the world.
Yes.
Considering all the famous people who were there, it was just incredible.
So did you discover any unknown work that was truly remarkable on that trip, since we were not aware?
Well, there were good talks at the Congress. In particular, there was a talk by Calderon, which appeared in the proceedings of the conference in a 3-page paper. It's a remarkable paper. Detailed proofs were never published, though people in the subject know how to carry out the proofs. It's a very striking paper. It extends, see, what Agman and Douglas and I had done is to get LP estimates and domains. He poses a problem on the boundary and uses singular integral operators on the boundary. And something called Calderon projection.
Yes.
It's a very striking paper. He was, in my opinion, a very remarkable mathematician.
Indeed.
In 1963, after going to Novosibirsk, I stopped in Moscow for some days, and I attended Gelfand's seminar.
Did you give a seminar there?
No, on that occasion I didn't, no. And this is it's a big show. I mean, it's a theater. It's a 3-hour affair. There are several different speakers, and what Gelfand does is interrupt each speaker and say, Yasha, you're not explaining things well. No, this is really what you mean to say. And he talks for 10 minutes, and then turns to somebody in the audience and said, what do you think? Isn't this? The person obviously had been sleeping and didn't pay attention. So, but anyway, Gelfand did this with every speaker, and he was just known to do this all the time. He just wanted to clarify things with his way of seeing it. And it was really a remarkable experience to see that. And when we left, Friedrichs, who had also attended, said, we should run a Gelfand-style seminar at Courant Institute, and we'll take turns playing Gelfand.
Were all the speakers Russians at Gelfand?
On that occasion, all the speakers were Russian, yeah. So they spoke in Russian, and I had a friend, one of the Russian friends, sitting next to me translating.
I see.
Yeah, and then he had a birthday party. It was in September, and it was his 50th birthday party at his home, which I attended, and it was a very warm and wonderful experience. My early work was mainly, aside from my thesis, was mainly in linear partial differential equations, and at some point I started to work in nonlinear. And one of the reasons was I found developments in linear became extremely technical, enormously technical, and I just found I couldn't quite keep up with it all. And after working in nonlinear, you could do simpler things, make advances with simpler ideas and nonlinear problems. And since then I've worked almost entirely, not entirely, but almost entirely in nonlinear problems.
But wouldn't you say also that the fact that the nonlinear problems arise naturally from your love to geometry?
Oh yeah, and even today they're beautiful problems coming from geometry. Yeah, wonderful problems.
one has to
wonderful
deal then
source.
with the nonlinear problem.
Yes, and of course in physics, I mean classically, so much of mathematics came from physics,
Yeah.
and still comes from physics. And physicists have wonderful mathematical ideas. I have great admiration for physicists. Mark Katz, a mathematician, once gave a talk at Caltech, and Feynman, famous physicist, introduced him. And he said, "We're happy to have our speaker, mathematician Mark Katz. You know, without the help of mathematics, developments in physics might have been delayed by a week." And Mark Katz said, "Yes, that was the week the world was created."
There's some work you did on pseudo-differential operators.
Oh,
So
yeah.
you want
That
Tell
was,
us a little
I
bit.
started work with Joe Cohn. Joe Cohn had done his famous work on regularity at the boundary for the
Right.
so-called D-bar-Neumann problem.
Right.
This is an elliptic problem where the boundary conditions are such that the usual elliptic theory does not apply. Usual elliptic theory, you can get the full regularity of solutions. Here you lose some regularity, but you still show regularity. So Joe Cohn solved that problem. Beautiful piece of work. And together we thought, can we extend this to more general systems? This was for, so D-bar-Neumann, do something more general with this kind of boundary conditions which are not good enough for the regular elliptic theory.
Right.
So we started to work on that using estimates, multiplying functions, integrating by part. And we had to use singular integral operators of Calderon and Zygmunt. And what we needed was commutator of singular integral operators.
Right.
And we needed the properties of that, and that wasn't in their theory. So we said, well, we should be able to do something. So we worked out something more general, an extension of what Calderon and Zygmunt did, which is an algebra of such operators. So products, commutators, so on, all lie in that family. So you look at a commutator of such operators, and you get such an operator plus lower order operators with explicit expressions for those. And it's like the Lorentz formula for multiplying two differential operators. So you get lower order terms, explicit formulas. So we did that, and we did it for this problem in order to prove regularity for these kind of boundary value problems. That was the reason we did it. And then we did some other papers on regularity for, so we did a paper on parabolic equation, regularity for that.
Been talking about problems, working on problems. So, but somehow all of these problems, in one way or another, were fundamental and proved to be very influential in the theory. So, how did you always manage to come up with such problems? I mean, usually people have difficulty; they build theories, but you solved problems, and from the problems came huge theories that were developed afterwards.
I don't know. First, you're exaggerating.
I'm not exaggerating. That's the truth.
But I don't know. You work on problems that you like, that catch your fancy. I once was visiting France, and some young man who was a graduate student came up to me, and he said, "How do you find a problem to work on?"
Yes.
And I said, "Well, I don't know quite how to answer that question, but it's happened to me sometimes that I've read some proof, some known theorem, and I didn't like the proof. And so I started to think about it, and then this led to something new." So he said, "I never found a proof I didn't like." And I thought, the guy's hopeless.
That's probably true. That's probably true.
But how to choose good problems, I don't know. Brésis is terrific at coming up with problems.
True. That's
We
also
sit
another
in a
example.
talk together, and any talk he hears, he comes up with new problems. So he's wonderful with students. He's had marvelous students, incidentally. And he's wonderful at proposing problems to students. They just come out of thin
But
air.
you also had marvelous students. How many students did you have?
I had 45. Oh, that's one of the joys of being a mathematician, having good students.
Right. And
You learn from them more
Yes.
maybe than they learn
Yes.
from you.
Yes. And you managed not only to have many good students, but also many friends in the years, in mathematics and otherwise. I know that.
Oh yeah, the mathematics community, I think of as a family, and you go to some other country and you're part of, you meet other members of the family and you're immediately at home with them, and it's a wonderful thing, absolutely marvelous thing.
And also, you've been, myself included, a great supporter of young people, not only who came to the institute, but everywhere. I should tell the story, if I may, about you, Professor Nierenberg. I was just barely finishing my postdocs here, and you were supposed to give a lecture at Collège de France, and the amphitheater was filled, and people were flooding through the amphitheater. And then you started your lecture, says, "Oh, I'm not going to talk about my work. I'm going to talk about the work of a young professor at Quran, Jalal Shatah, and Henry McKean." And I remember it. I mean, here I am just starting in mathematics, and you elected to give the exposure to other people than yourself. And you always have done that throughout your life. So that's very
I
kind.
didn't remember that.
I remember it because you've done it so often that you don't remember.
Well, let me tell you, in connection with that, I once was at Berkeley invited to give a talk, and I said, I'm going to speak about a paper of Paul Rabinowitz.
Uh-huh.
And they said to me, next week Paul is coming and he's speaking on that paper. So when I got home, I called Paul and I said, begin your talk with the following story, which is a story I heard in Moscow many years ago. At the Writers Club, they used to show foreign films which were not shown commercially. So they were not dubbed and they had no subtitles, and they would have somebody translating simultaneously.
Mm-hmm.
And so once they were showing a French film, and the usual French translator was not there. So they said, is there somebody here who speaks French? And a mathematician got up. Yeah, I know some French. So he began to translate. But he didn't know French very well. He made up a story. And he was very witty, amusing. At some point, it looked as though the guy's about to marry his sister, but he somehow got out of that. He managed very well.
Changed the
The
story.
audience loved it.
Yeah.
They demanded that it be shown again next week.
Oh.
Next week, the real translator was there. They booed him. So Paul did begin his lecture with this story.
With your work on fully nonlinear system, was that also involve some of your students?
Cabret, in particular, worked on nonlinear equations. Yan Li worked on nonlinear equations. Did several problems in his thesis.
You had many students. I mean,
I had 45.
That's many in my book. That's
Some people have had considerably more. I met a French mathematician who has had 103 students. You can imagine that.
no, that's difficult to.
It's Roger Temam.
Yeah, I know Roger well.
Yeah, so some of the theses are sort of computational,
Yeah.
but nevertheless, it's incredible to have that many PhD students.
Yeah. That probably would require less close work, collaborative work. I mean, I've seen you work with your students. They come to your office often. There is lots of collaborative
of course.
work, good
Sure,
rapport.
lots
You
of
spend good
discussion.
time with them. That's what.
Certainly, that's what one normally does, yeah.
Some thoughts about your career being all at the Courant Institute.
Yes, I came, as I said, as a graduate student in 1945, got my degree in 1949, and have just been there ever since, which I consider enormously good luck. I think I've had a very lucky life on the whole, getting the way I got there and having wonderful colleagues, wonderful students, wonderful friends in the world. It's, mathematics family is not a very big, but a very nice, warm family. Something really, to my mind, something really remarkable.
It is. It is.
I find mathematicians on the whole non-competitive, although some people don't agree with me. Some people say, yes, mathematicians are competitive.
Well, I would not agree with you, use mathematicians, but I definitely would agree with you in the environment of Courant. And people at Courant are not everyone competitive. But as a whole, the mathematical community, you find your collection of competitive mathematicians.
Well, there are some, of course. There's a joke about one mathematician says to another, that thing you proved, it's trivial, and I proved it first.
And he's a friend.
No, it was not. It was somebody else. He didn't say it to me. He said it to.
No. And your friendship with Peter and Kathleen dates back.
Oh yeah, it was a wonderful group of graduate students. When I came, or the year after, there was Joe Keller was there, Martin Kruskal, Peter came the year after, Kathleen came half a year later. It was Avron Douglas came shortly after. It was an excellent group of graduate students. Harold Grad.
It's almost a singular point in time where you have such a good collection of students in the same place.
And that Courant kept them.
Right.
Not the usual tradition of sending students away after they graduate, but he kept the good students.
You interacted with Richard Courant, although Stoker was your advisor and you talked a lot with Friedrichs.
Yeah.
How was Richard Courant?
Well, I had good relations. We didn't interact so much mathematically. He was wonderful with young people, and he would invite them out for dinner at his home and to help weed the Courant garden. And there were always music at his home, always. He played the piano. His wife played several string instruments. There was a joke that when Courant interviewed somebody for a job, he would ask them if they played an instrument. If they played the piano, he didn't hire them. But he was terrific with young people, really.
Yeah. Well, you kept the tradition as well as others, that since I came to the Institute.
Well, on the whole, I think we've somehow kept this tradition, the faculty, yeah.
Very, very good.
And Peter Lax has been like a brother to me all these years.
And this was one of the striking parts of the Institute when I first came as a postdoc, that there was still an atmosphere of family among the faculty.
Now the faculty is bigger. There seems to be much more applied mathematics than before. Courant and Friedrichs believed that there's no separation somehow between pure and applied. And now we have many applied seminars at Courant Institute.
Yes, the subject has branched in many directions, so it's quite different.
In fact, some time ago, a mathematician said to me, who works in partial differential equations, he said, "Is it still a field?" He said, "It has split in so many directions, it's not clear that there's still such a field." No, I think there is still such a field there.
Yeah, but he has a point in the sense that there are specialization within the subject of partial differential equations that people don't learn that all the field as we did.
We had visitors from Russia, of course, over the years.
Yes.
And at one time, Olenek, a Russian woman, mathematician, was visiting, gave a series of lectures.
Yes.
And she complained to me after a while that Peter Lax is sleeping in her lectures, which he often does. So at her next lecture, Peter wrote something on a piece of paper and passed it around. And it said, "We, the undersigned, testify that Peter Lax has slept through some of our best lectures." Everybody signed it, and it was given to Olenek at the end of the lecture. I told her she should frame it.
Yeah, indeed.
I was attending a seminar with Peter Lax, and midway the speaker said, "Now I come to the boring part." And Peter leaned over and said, "Oh, that he covered already."
But there are many jokes. In fact, I throughout, since I've known you, you love to tell jokes.
It's
And
true,
you are
I
a
do
good
like to
source
tell
of
jokes.
jokes for me. I use many of your jokes on many occasions.
But I've learned
Where do you
most of
get them from?
From Peter. Peter has a huge collection of jokes. So almost every joke I learned from him. And once I was telling a joke that I learned from him, and the listener said to me, "Why do you suddenly have a Hungarian accent?" Because Peter has a slight Hungarian accent. I was once on a committee of the National Science Foundation, and the chair of the committee said that he was requested to ask the committee to try and formulate a 5-year plan in mathematics,
Soviet style.
Soviet style. So I told an old Soviet joke about the first 5-year plan.
Yes.
So a member of that committee says, our first priority must be every family has a car and every family has a radio. Comrade, why is this first priority? Well, for example, if they announce on the radio that there's bread available in Kiev, you get in your car, you drive to Kiev.
I know you don't particularly like to talk about projection or what is this, but one thing maybe we did not touch on is the state of mathematics and the students going into math nowadays in the U.S. Do you have thoughts about this? Is there a difference? Do you feel that developing a new area in math, such as financial math or math economics, is influencing the culture of math and the way we do it?
Well, I think it will. So far, I think mathematical economics has not really influenced very much in mathematics, but it may. In the future, there may be very interesting problems coming from biology.
Right.
You know, Gelfand spent for years half of his time working in problems in biology as well as in mathematics.
Right.
And, you know, every time I visited the Soviet Union, I would see him, and I was each time embarrassed because he would, on each occasion, he would ask me, what is your view of what are the important problems today in mathematics?
Yes.
And I could never answer him. Somehow I didn't think in such terms. He did, but I didn't.
Okay.
So even today, I cannot say what I think are the important directions. I wish I had read more.
Mm-hmm.
There's such a thing as reading too much.
Right.
I remember John Nash advised young people, don't read too much, use your own ideas. But I feel I didn't read enough.
Mm-hmm.
I would have liked to have learned more mathematics. I always found reading mathematics hard. And today, at my age, I find it practically impossible. I read only what I absolutely need for my research, and otherwise I just can't read mathematics. So I remember a story of Friedrichs years ago. He said he has to read some paper in Russian,
Right.
mathematics paper, and Peter Lack said to him, isn't the Russian difficult? He said, no, it's not the Russian that's difficult, it's the mathematics that's difficult. With the new development, string theory and connections with algebraic geometry, I wish I knew that. I wish I could understand and see what people are doing. It's just beyond me. It's even very hard for me to keep up with developments in my own field now. Even in my narrow field, there's so many people working, there's so much work being done. It's just incredible.
But this is the nature of the beast, in
Yeah,
the sense that the
exactly.
mushroom,
There are many more people working, so
it's almost impossible to do
Yeah.
that nowadays. But
But how things will go in the future, I'm terrible at predicting. Just as I'm terrible at predicting politics, I'm terrible at predicting how mathematics will go. I would encourage young people, not just students, but also faculty, to collaborate, work with others. That's an enormous joy.
right. Well, you have
In
enormous
fact-
number of collaborators.
Oh yeah,
all your-
almost practically all my papers are joint papers.
Right.
But recently there was this striking story of this British mathematician Gowers,
Yes.
who put out a blog in which he said, there's an important theorem in number theory, I forgot by whom. The proof is very complicated. There has to be a simpler proof. Please, anybody with ideas, send contributions. About 100 people put out blogs on this problem, including Terry Tao, and eventually a simple proof was found. Incredible. This may be a new way of doing mathematics. Involve 100 people.
100 people contributed
Contribute.
different ideas to this to Gower's question.
Put out blog contributing ideas to this question. And putting it all together, we came up with a simple proof. It's amazing.
I don't read blogs, but
I don't either, but this may be a new way of...
Maybe I should start reading blogs.
Maybe a new way of doing mathematics. You put out a problem somehow and say, everybody, feel free to contribute to the problem.
It's culturally very different than the way you used to do.
Oh yeah, very different. I mean, I work with 2 or 3 people, and
Right.
Incidentally, we talked about complex analysis.
Yes.
There was a paper with 4 authors,
Yes.
Caffarelli, Spruik, Joe Kohn, and myself.
Yes.
And that was about complex Monge-Ampere equation, solving boundary value problem involving complicated estimates, maximum principle.
The usual.
As I've often said, I've made a living from the maximum principle.
Right. Well, you work in many parts of differential equation, but I know that somebody referred to you once as an elliptician.
Yes, that was André Weil called me an elliptician, not to my face, but anyway, he called me that, and I thought it was a fair remark. Yes.
Well, I don't. Okay.
It didn't bother me. I wish I knew more physics. I wish I knew what the theoretical physicists were doing. They introduced some wonderful mathematics, and mathematicians have taken these up, and they've led to wonderful problems. Supersymmetry, string theory. Many physicists don't believe that string theory leads to real physics because it doesn't suggest experiments. But it's led to wonderful mathematical problems.
Right.
That both mathematicians and physicists have worked on.
Right.
And physicists have really introduced new ideas in mathematics, and unfortunately I can't keep up with that. I mean, at my age I find it so hard to keep up with anything anymore. But I would certainly encourage young people to work in some problems in that direction.
Now, this is, I presume, the work in high-energy physics of Vafa and Witten and
Yes,
alike.
exactly.
And if I take it now, is that the high-energy physics, I think Richard Courant was interested in that and tried to hire physicists at the Institute, I was told.
He did hire, there was a physicist named Bruno Zumino. We became very close friends. Eventually he went to Berkeley.
Right.
And yes, Courant did try to develop
This relationship
yes,
between math
yeah.
and physics.
and he encouraged Moser to work on some problems connected with physics.
There are new areas in mathematics that are developing now, which I would say were in their infancy when I was doing math, started to do math, in work that's related to computer science. Do you find some of this work also intriguing?
Well, I wish I knew more. I just don't know enough to judge it or to make any comments about it. I should say that when Peter Lax and I were students, he always knew more mathematics than I did, and that continued throughout our life. And very often he would explain something to me, and sometimes I would forget and ask him to repeat. And once he said, "You know, I'm happy to explain things to you several times, not more than 10 times."
That sounds like Peter. It's
Yeah.
a Peter joke.
Developing general theory people are not doing that so much nowadays.
Yeah.
However, there's one big subject within partial differential equations that has hardly been touched, and that's so-called overdetermined systems, meaning more equations than unknowns.
Right.
So the main development in that is due to Cartan and Kähler.
Right.
And they assumed everything is analytic and used Cauchy-Kovalevsky. If you don't assume analyticity, we don't know what are the well-posed problems. You need compatibility relations.
Right.
For instance, Spencer and Goldschmidt did a lot of work and algebraic work connected with these overdetermined systems.
Right.
But there's no analytic work been done. And these kind of systems arise in geometry, often. More equations than unknowns.
Right. Through your career, I know you won many awards, several of them. The Chern Prize, the Crawford, the Congressional Medal of Science, and so on. And maybe you want to share some of the experiences of when you won some of these awards.
Well, of course, each time it's a great honor. When I received the National Medal of Science, it was awarded by President Clinton.
Yes.
And there was a reception at the White House, and we were able to visit a number of rooms in the White House, and there is my grandson running around in the White House with a medal around his neck.
Great.
And Clinton was very warm, and he and Gore were there, so both were very warm. Lovely occasion. The Crawford Prize, that was a Swedish prize,
Right.
which they award to different subjects every year.
Right.
In mathematics, it's roughly every 5th or every 7th year. And I shared the first prize with Arnold, a Russian mathematician who was a good friend.
Right.
And he was not allowed to go get the prize. Soviets didn't let him go. He got it only years later. It involved some money, and he got it only years later, when he was allowed to travel.
And the Chern Prize?
The Chern Prize was, again, a marvelous honor. Chern was an old, very good friend for many, many years. We often had dinner together in his home or in my home and in restaurants, and it was always a pleasure to talk mathematics with him. I wrote one paper with him and Levine, and that was in complex analysis, come to think of it. And it's a paper I think that nobody uses at all. But it was to find some intrinsic norm at cohomology classes, but I think nobody uses that norm.
Wow.
But anyway, it was fun working with him.
Yeah.
But another geometry paper was with Loevner. Loevner was a mathematician at Stanford,
Right.
a wonderful mathematician, and he came originally from Czechoslovakia. And the same summer that I worked with Chern, I worked with Loevner on a problem that he formulated. And that was an enormous pleasure. Problem in geometry, but involving, of course, partial differential equations.
So of the classical topics in mathematics, would you say geometry is one of your favorite?
Oh yes, definitely. Geometry and complex analysis
Are your favorite?
are my favorite. Yeah, absolutely.